All right, let's get right into it. We're going to talk about a side of NASA that, doesn't always get the big headlines. It's this incredible mission that has totally changed our world, not way out in the cosmos, but right here, inside our own atmosphere.
Just for a second, when I say the word NASA, what's the first thing that pops into your head? For pretty much everyone, it's something huge, something out of this world, right?
Exactly. You're probably picturing the space shuttle thundering off the launch pad, or those unbelievable pictures from the Hubble telescope, maybe even astronauts bouncing around on the moon. And yeah, that makes total sense. Those are some of the most amazing things humanity has ever done. NASA is our space agency, after all. But what if I told you that for every single one of those giant leaps in space, NASA, and actually its predecessor, an agency called NACA, was also making these game-changing breakthroughs in aeronautics. Breakthroughs that literally affect how you and I fly every time we get on a plane. So let's uncover this hidden mission that completely reshaped our skies. Okay, first stop, the jet age. This was a time of incredible optimism, but also one massive, and I mean massive problem. Pilots were pushing planes faster than ever before, but they kept slamming into what felt like a very real, physical wall in the sky, the sound barrier. So what was going on? Well, the culprit was this phenomenon called transonic drag rise. See, as a plane gets close to the speed of sound, the air flowing over it starts to create these shock waves. And those shock waves generate this huge, violent spike in drag that could literally shake an airplane to pieces. And listen, this wasn't just some abstract theory. The Air Force was building this brand new, state-of-the-art fighter jet, the Convair UF-102. It was supposed to be supersonic, but in testing, it failed. No matter how much power they threw at it, the plane just got stuck. It could not get past Mach 0.98. It was right there on the very edge, and it just couldn't do it. So, how do you fix a problem like that? Well, this is where a NACA engineer named Richard Whitcomb comes in. While everybody else was thinking about bigger, more powerful engines, he had this completely counterintuitive idea. He figured out the drag wasn't just about the wings, it was about the total shape of the plane from nose to tail. His solution, called the area rule, was to literally pinch the body of the plane where the wings were, creating this, Coke bottle shape. And just like that, the airflow smoothed out, the drag disappeared, and the redesigned jet sliced right through the sound barrier, no problem. And this discovery didn't come easy. Whitcomb was so obsessed with solving this, he was running wind tunnel tests for 16 hours a day. He got so tired of the commute that he just brought a cot into the lab and slept there. Now that is the kind of passion that breaks down walls. Okay, so you solve one problem, and almost immediately, another, even scarier one pops up. Once we started going to space, we had a new challenge. How in the world do you get back home without burning up on the way down? Re-entry is basically like flying into a furnace. Just to give you a sense of what we're talking about, we're looking at temperatures over 2,000 degrees Fahrenheit. I mean, that's just insane. That's what the space shuttle's aluminum skin had to deal with. So to protect it, NASA came up with these incredible silica tiles. They'd bake them at that crazy temperature, and it would turn them into these super lightweight bricks that were mostly just empty space, making them unbelievable heat insulators. But the tiles were only one piece of the puzzle. The other piece was, once again, totally backwards from what you'd expect. Logically, right, you'd think a sharp, pointy nose would be the best way to slice through the atmosphere. But a NASA scientist named H. Julian Allen proved the exact opposite was true. A blunt nose creates this huge shockwave that actually stands off from the vehicle, and it pushes the absolute hottest, most intense plasma away from the spacecraft's skin. It basically uses the air itself as a giant heat shield. Just brilliant. And the process for making each of those tiles was a marvel all on its own. They'd start with this goop, this slurry of pure silica fibers and water. Then they'd press it into blocks, bake it at that insane temperature, and finally, a computer would meticulously carve every single one of the more than 30,000 tiles because each one had to fit its own unique spot on the shuttle. It was like the world's most complicated high-tech puzzle. So we figured out how to beat drag, and we figured out how to beat the heat. But a new problem was starting to creep in. As planes got faster and faster, their designs had to get more extreme, and honestly, a lot less stable. We were building jets that were almost too wild for a human being to actually control. I mean, imagine being a pilot dealing with this stuff. You could experience something called pitch up, where the plane's nose just suddenly and violently jerks up into a stall you can't get out of. Or inertial coupling, this bizarre gyroscopic effect where a simple roll could send the plane tumbling out of control. These weren't just little quirks. These were deadly flaws that made these amazing machines terrifyingly unpredictable.
The answer was to give the plane a brain. The solution was digital fly-by-wire. Instead of heavy cables and pulleys physically connecting the pilot's controls to the wings and tail, the system turns the pilot's inputs into electronic signals. Those signals go to a computer, which then tells the control surfaces what to do. It's like having a smart co-pilot making thousands of tiny corrections every second to keep the plane perfectly stable.
And this technology didn't just show up one day. It was a whole progression. It started with simple mechanical controls. But then, in 1972, NASA flew this modified F-8 fighter jet with zero mechanical backup. It was flown entirely by a computer. That flight proved the concept was safe and reliable. And that one experiment paved the way for the systems used in the space shuttle, in agile fighters like the F-16, and in the incredibly smooth and safe ride you get on basically every single modern airliner today.
And that really brings us to the biggest point of all this. This isn't just a fun history lesson. These breakthroughs, they aren't just sitting in a museum somewhere. They are up in the air, right now, all around us. They're on your next flight.
Seriously, think about it. The same research that beat transonic drag led Richard Whitcomb to invent something called the supercritical wing, which is a huge reason modern airliners are so fuel efficient. That fly-by-wire system doesn't just make fighter jets do cool tricks. It's what makes your passenger flight so stable and safe. And NASA's pioneering work in advanced composite materials is why planes today are so much lighter, stronger, and more durable than ever before. So all of this really makes you wonder, right? What's next? The challenges today are things like hypersonic flight and electric airplanes. These are the new walls in the sky, the modern-day sound barriers. And you can bet that somewhere, that quiet, hidden mission of NASA's aeronautics teams is already hard at work, figuring out how we're all going to fly tomorrow.